Okay, so we're in section 10.3 right now. We're talking about polar coordinates. The topic of polar coordinates is something you cover in trigonometry, and for that reason, nothing in this section should really be brand new to any of you. This is review, and we're covering this here because in 10.4, the very next section, we're going to look at how to do calculus in polar coordinates. So to get into it, what are polar coordinates? Well, so far, everything that we have done as far as graphing curves and regions and things like that have been concerned, we've been working in one coordinate system, which we call rectangular coordinates. It's a two-dimensional coordinate system where points are represented as ordered pairs of the form x, y, where the x represents the horizontal displacement of the point relative to an origin, and the y represents the vertical displacement of a point relative to that origin. So we call that the rectangular coordinate system, and the reason for that is because it's easy to describe rectangles in that system. However, there are certain cases where that particular way of representing points in a two-dimensional space is not as convenient as some alternatives might be. And so this is where polar coordinates come up. Polar coordinates are better at describing certain types of curves, such as circles centered at the origin, or other curves that we're going to look at towards the end of this section, better than rectangular coordinates typically do. So we're going to go through the basics of how we think about points in polar coordinates and how we interpret the different symbols and things like that. So just like in rectangular coordinates, we're going to fix a specific point in the plane. Rectangular coordinates would call that point the origin, which the O here is still representing the word origin. But in polar coordinates, we give it a different name. We call that the pole. Normally in rectangular coordinates, I would draw an x and a y axis here through the origin, and then plot points relative to those axes. I can do the same thing here, but we're just going to focus on part of that. Specifically, I'm only going to show the positive x-axis here. That positive x-axis is what we call the polar axis in polar coordinates. Now let's say I have some point in two-dimensional space and I want to represent its coordinates using polar coordinates. Polar coordinates consist of two values, an r, which comes first, and a theta, which comes second. The r is the distance from the origin to that point. And I'm using the term distance a little bit loosely because we normally think of distance as being a strictly non-negative quantity. However, in polar coordinates, there is a way of interpreting r as a negative number, which we'll get to in just a moment. But that's the way we're going to think of r. It's the distance between our pole and the point itself. Theta represents an angle. So once I take my pole and the point we're talking about, P in this case, and join them by a line segment, if I measure the angle that line segment makes with the polar axis measured counterclockwise. This is the same way that we do this in trigonometry when we learn about angles and the unit circle and things like that. That value theta is the second coordinate in our new coordinate system here. Now, this coordinate system comes with some subtleties, some things that don't actually have counterparts in rectangular coordinates. One issue, in fact, it's not necessarily an issue, but one difference, I should say, is that polar coordinates, in polar coordinates, a point can have multiple different representations. So for example, if I'm in rectangular coordinates and I'm thinking about the point 1, 2, there's nothing else that I could call that point in rectangular coordinates. 1, 2 is what it is. There's no alternatives. In polar coordinates, the same point can have multiple different representations in polar coordinates. So here's the way that can happen. First of all, because one of our coordinates is an angle theta, which we're going to be thinking of in radians, we know from trigonometry that we can have what are called coterminal angles. Basically what that is if I take this line segment here that connects the pole to this point, if I add 2 pi to the angle, it's going to swing that line segment all the way around and land me right back in the same position. So this point would still be in the exact same place. However, having added 2 pi to that angle, I now have a different theta that I'm using to represent this coordinate here. So one way of kind of generalizing that is to say that if you have polar coordinates r theta for some point in two-dimensional space, then r theta plus 2 pi n, where n can be any integer, would be alternative coordinates for the exact same point. Because again, for whatever integer I'm putting in for n right here, that's just telling me how many clockwise if it's negative, counterclockwise if it's positive, rotations I'm making and still getting back to the same point. Okay. Another thing that needs to be mentioned with polar coordinates, which I alluded to before, is that the r can be negative. And the way that we interpret negative values for r is we would still take its absolute value to determine the distance between the pole and our point, but we think of the positive version of this as being 180 degrees away through that angle there from the negative version. So here, if I have the point r theta, and I want to compare this point to the point negative r theta, I would just take the line segment here connecting the pole and my point, and I would add pi, or 180 degrees, to that angle, swing this thing around, and essentially what I get is kind of like a reflection of sorts. This point reflects through the origin to this point over here. So we do have a way of interpreting those negative values for r. Okay, so let's do an example where we're just plotting points. Now what we have here is what's called a polar grid. In this polar grid, if you notice, there's a vertical line here and a horizontal line here. Those would correspond to the y and the x axes if these were in rectangular coordinates. However, normally if we're plotting points in rectangular coordinates, I would then label my axes along the horizontal and vertical axis here with some numbers, 1, 2, 3, 4, or whatever scale I want to use. That's not a very helpful way of plotting points in polar coordinates, though, because polar coordinates represent give me information about distance from an origin and an angle that the point creates with the positive x-axis or the polar axis. So something like this, where we have concentric circles centered at the pole like this, and then I like to think of these as spokes, like in a bike tire, but really these are lines through the origin forming different angles with the positive x-axis. This type of a grid is a lot easier to plot points in polar coordinates with. So first example, I want to plot the point 3, negative 2. What I would do is I think it's a negative 2, pi over 2. I would find the angle pi over 2. Notice it's labeled here. And I would align myself with that spoke or that line. And then 3, I'm going to think of as 3 units along that line, which I use these concentric circles to count out. So 1, 2, 3. This right there is the point P. Okay? Taking another point as an example, I want to plot the point Q, 2, negative 3 pi. So negative 3 pi, I think of this exactly in the same way I would think of angles in trigonometry. If an angle is negative, I simply measure that relative to the positive x-axis, but moving clockwise instead of counterclockwise. 3 pi is also greater than 2 pi, so this means I'm going to go more than one full revolution around this circle. So to find negative 3 pi, I would go here to 0. Negative 2 pi would take me all the way back around to where I started, and then another negative pi would land me here. So negative 3 pi is coterminal to pi, meaning it takes me to the same position relative to that angle. Now what I want to do is look at the value of r. It's 2, so I go 1, 2, and I find that here. That's Q. Let's give it a label. Next one, r. R is the point 0, 3 pi over 4. Now this one's interesting because this is a case where we don't really even need to know what the angle is. Because, if I tried to find 3 pi over 4, I could find it right here. But this is telling me that I'm 0 units away from the pole. So the pole, again, that's the origin. And if we're 0 units away from it, then we are literally at the pole right there. Okay? So this is an interesting one because I would have gotten the same point regardless of what angle I put here. When r is equal to 0, theta is irrelevant because we still get the same point every time, okay? Finally, we have this point here, s, negative 5 pi over 6. So again, I would find 5 pi over 6 first, which is here, okay? And then we will have a negative 5 for r. So remember that negative 5 means that instead of actually going on this spoke right here, I want to add 180 degrees to take me to this one. And notice if I take 5 pi over 6 and I kind of follow it through the origin, I can see where that would land over on this side. And then I'm going to count 5 units in that direction. 1, 2, 3, 4, 5. That puts me on this blue circle here. So that would be the point S. Okay? So that's just a little bit of kind of getting familiar with polar coordinates. Now let's come down here. So now that we have plotted some points and talked about how to interpret r and theta in polar coordinates, our next order of business is to figure out how to relate that r and that theta back to the x and y that we would use in rectangular coordinates for the same point. So say we have this point P here, and we're going to represent P both in polar coordinates and in rectangular coordinates. So if the coordinates of P are x, y in rectangular, then if this is my point here, x is the horizontal displacement from the origin, y is the vertical displacement from the origin. So I can think of them as two legs of this right triangle here. R would then have to be the hypotenuse of that right triangle because it's the actual distance from this origin or the pole to our point. Finally, theta is this angle right here. So what we've created is a right triangle that contains all 4 coordinates from those 2 coordinate systems, and we can use right triangle trigonometry to relate them all together. So first of all, here, if I were to take the cosine of that angle theta, cosine is adjacent over hypotenuse, which in this case is x over r. This, I could solve for x, and I get x equals r cosine of theta. So that's one of these conversion formulas that we can use to relate these coordinates. I'm going to zoom out just a little bit. There we go. Same thing with sine. If I did sine of theta, it's easy here to see that that would be y over r, which tells me that y is equal to r sine of theta. Okay, so that's where these 2 conversion formulas are coming from. And these are useful if you know the polar coordinates for your point and you want to get the rectangular coordinates from those. This is for going the other direction. If we know the rectangular coordinates, but we want to translate that into polar, I have these formulas here. Notice that r squared would be equal to x squared plus y squared because that's the Pythagorean theorem applied to that right triangle. Also, my angle theta, if I want to relate that to just the x and the y here, I can take tangent of that angle, which would be y over x. So that's where this comes from. Okay, those conversion formulas, you probably already have at least these ones memorized, probably this one as well, just from trigonometry. But there they are again. So let's use them now to do some conversions. I want to convert the point 9, 5 pi over 4 from polar to rectangular coordinates. So this is polar coordinates here. In this case, I have r equals 9, theta equals 5 pi over 4. So my conversion formula says that I take x and set it equal to r cosine of theta. That's 9 times cosine of 5 pi over 4. Now, cosine of 5 pi over 4 is negative root 2 over 2. So this would be equal to negative 9 root 2 over 2. Okay? Y is equal to 9 sine of 5 pi over 4. Remember, it's r sine of theta. That's where y comes from. Sine of 5 pi over 4 is also equal to the same thing, negative 9 root 2 over 2 after multiplying that 9 with it. So putting those into the ordered pair notation, I have negative 9 root 2 over 2, negative 9 root 2 over 2. That's the coordinates in rectangular for that point, okay? Now let's go the other direction. I want to convert the point 6 root 3, negative 6 from rectangular to polar coordinates. So the easiest part of this is getting r. R squared is equal to x squared plus y squared. So that's 6 root 3 squared plus negative 6 squared. Okay? This is equal to, so I have a particular way I'd like to do this. I know that 6 squared is 36. And then when I square root 3, I'm just going to get a 3. I'm intentionally not multiplying these things together because I'm going to do something a little bit different. Now if I square that 36 right there, I get plus 36. So this is like 3 times 36 plus another 36, which is the same thing as 4 times 36. It's just kind of a mental math sort of a thing that helps solve a problem like this. This comes out to 144. Now that's r squared, it's not r. So this would imply that r is 12 because we can take a square root. Okay? Now, again, there is a way of interpreting this same point by making r negative 12. I could do that as well because remember, in polar coordinates, the same point can have all different kinds of representations depending on how we manipulate the r and the theta. But I'm going to go with kind of the natural solution to that, which is positive 12. Now we have that other conversion formula that says that tangent of theta is equal to y over x. So that's negative 6 over root 3. 6 root 3, sorry, there's a 6 there as well. The 6's cancel, giving me 1 over root 3, which simplifies or rationalizes to negative root 3 over 3. Now, if you think about this for a moment, it's tempting to just say, okay, take an inverse tangent of this and see what my calculator tells me, or see what I can figure out from my knowledge of the unit circle. But the issue with that is the inverse tangent function may give you the wrong angle here. And the reason for that is when we define the inverse trig functions in trigonometry, we put restrictions on them. In particular, we restrict their ranges, so they can only spit out values within certain quadrants. The tangent function, or the inverse tangent function, only gives me angles between negative pi over 2 and positive pi over 2. And if you remember from trigonometry, there's a specific reason why we do that. But that's great that that's only quadrants 4 and 1. It's possible that the point that I'm having or converting here, the point that I'm trying to convert here lives in quadrant 2 or quadrant 3. And just using an inverse tangent function directly, I would miss that. So what I'm going to do instead is I'm going to think, what quadrant does this point actually live in? Well, I have a positive x value, but a negative y value. That would put this in quadrant 4. So luckily, in this case, if I did take an inverse tangent directly, I would get the correct angle. But if this negative was over here, then I have a negative x, positive y. That would put me in quadrant 2. I'd have to be a little bit more careful. So let's think of it now, in this context now. Inverse tangent of negative root 3 over 3 would give me the value of theta that I'm looking for. That would be negative pi over 6. I could also call that 11 pi over 6 if I wanted it to be positive, or remember, there's all different kinds of things we could do there. That means this point can be represented as 12 negative pi over 6 in polar coordinates. Okay, cool. So the next thing that we're going to do, and we're going to do this in the next video actually, is talk about polar curves. How do we interpret polar curves? So let's jump to the next video for that.